Okay, geometric sequences and series. The first thing I probably need to write is the formula that you're given here at the top. Let me go ahead and write that in here. So remember our nth term, a sub n, is equal to our first term, and we're going to multiply that times a common ratio. All right, and then we're going to raise it to the power of n minus 1. So if you were to plug in, 1 for n, that would be the first term we're looking for in the sequence. Well, 1 minus 1 is 0, which would be r to the 0 power. R to the 0 power would be 1, so you can see a sub 1 times 1 is a sub 1. That's why this has to be an n minus 1 right here at the top for exponents. So it's very similar to our arithmetic. Other than that, in fact, we're multiplying instead of adding or subtracting. So just like we did with the other notes, I'm going to do the first two parts of example 1, let you do the third part. So just find the common ratio here between these terms. We're multiplying by 3 each time in order to get from one term to the next. So we would call our common ratio equal to 3. Now part B, you could do that one probably pretty quick as well, but just in case you weren't able to do it in your head, because there might be some later on that you can't. If you're looking for, first of all, let's establish that this is geometric, and you're not sure what that common ratio is, you would take one of the terms, say 20, and divide it by the term before that, so 10. So you can see our common ratio is 2 for part B. And I'll let you do part C, working with fractions. And I think it's also, let me look at it real quick. Yeah, you have an alternating with a sign, so your R is probably going to be negative. I'll see what you can do in that and check your notes, the notes key on Canvas. All right, example 2. List the first 5 terms of a geometric sequence, given that we have 2 as our first term and our common ratio is 4. So, very simply, we just listed out. So 2 obviously is given to us, and then we're going to multiply by our common ratio every time in order to get to the next term. So 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. And then 128 times 4 would be 512. All right, example 3. Find the nth term of the geometric sequence. Find the 9th term of our geometric sequence. And we're given the first term is 4, and our common ratio is 0.5. So obviously, I like working with fractions, so I'll just call that 1/2. And we're looking for our 9th term. So I'm going to rewrite this formula from the beginning. Okay, that's just our generalized formula for geometric sequences. So to find the 9th term, we're going to plug 9 in for n. Our first term is given to us, it's 4. And then our common ratio is 1/2. And we're going to go to the 9 minus 1 power. So obviously we're going to be saying what's 4 times 1/2 to the 8th power, which I believe is 1 over, let's see, 2 of those 2's would be gone. Should be 1 over 64. All right. Example 4. First thing it wants us to do is write the nth term formula, given this particular sequence of numbers. Well, first thing we need to do is figure out what r is. So it'd be -2 over 6. So it looks like our common ratio is -1/3. If you were to divide 2/3 by -2, you see the same thing. We're multiplying -2 times -1/3. You get 2/3. So there's our common ratio. So first thing is writing our nth term formula. So a sub n is equal to our first term. Well, our first term in our sequence given here is 6 times our common ratio, -1/3. And we're going to go to the n minus 1. So there's the first part that it wanted us to get. Okay, and then it says use that formula to determine what the 10th term in that sequence is. So we're going to plug in 10 for in place of n, so substitution. All right, so that's like 6 times -1/3 to the 9th. All right, so it looks like our 10th term on example 4 is going to be -2 over 6,500 61. Okay, example 5, it gives us this gap again. So we have a second term, or for the first time rather, we've been given the second term, we're given the fifth of a geometric sequence. What is the sixth term? Okay, so first thing we're thinking about here is if we had, let me just display it this way. If you had negative 18 as our second term, to get to the third term, we would basically take our common ratio, whatever that happens to be, our R value, and multiply it. So it'd be negative 18 times R. And then to get our fourth term, we would take negative 18 and R and multiply it again times R. So now it would be R times R, which is R squared. And then to get our fifth term, we would take negative 18R squared and multiply that by R again. So R squared times R would become R cubed, which is what we're looking for. So our fifth term is taking negative 18 and multiplying it times R cubed, and that would give us the 2/3 it's given to us. So negative 18 R cubed is equal to 2/3. All right, because the fifth term is equal to 2/3, and the fifth term is equal to negative 18 R cubed. We can solve this equation to figure out what R is. So if we would divide by negative 18, that would be, let's see, negative 1 over 27, because a 2 and 18 would just simplify to a 9. So 3 times 9 is 27. And then we're going to take the cube root of negative 1 over 27, which is negative 1/3. Okay, so in example 5, we now know that R is negative 1/3, and the question is, what is the sixth term in our sequence? Well, our sixth term would simply be our fifth term, 2/3, times our common ratio, negative 1/3. So we're looking at negative 2 over 9 as our sixth term. Okay, let's get into the sums now. So we have our geometric sequences, what we did with earlier. Now we're doing geometric series. Now, the geometric is a little bit different than arithmetic. We have two formulas. So the first one is if your series is finite. Okay, so remember, finite means it ends, it doesn't go on forever. We have an exact number of terms that we're working with. So this would be the formula if we're going to be doing that. So, our first term, our common ratio, and then n would just be the number of terms in our series. But then we also have infinite geometric series. And it's a little bit different formula, just a sub 1 over 1 minus r. So the same things as this one, but notice that this parentheses is taken out. Now there's one little stipulation that I need to make sure I say right here, is that you can only find the sum of an infinite geometric series if our common ratio is between negative 1 and 1, not including negative 1 and 1. Okay, so if our ratio, for instance, was 2, then we would not be able to find the sum of that geometric series, and we would just say that the series diverges. But if it is between negative 1 and 1, essentially the sequence of numbers in the series gets smaller and smaller and smaller, not necessarily by sign, but by the value, the absolute value of that number. Well, then we're going to be able to figure out what the sum of that number, sum of that series is. Okay, so first one, example 6 here. It's alternating series. Now this one's not too bad. You've done this before, where you could probably extrapolate this out and figure out how many terms are in this particular series and just plug it in. But just in case you do run into a series later on that you can't just do that in your head or do very quickly, let me show you just a general approach so that you can make sure that you do know how to solve this problem. All right, so we have everything we need except for the number of terms. So we're going to go to our generalized a sub 1 times r to the n minus 1 geometric sequence formula that we were using up to this for the first few examples in our notes. So our first term is 1, and then we can see, I'm not going to really worry about the alternating sign right now. I'm just going to approach it as if these were all positive terms, because the sign doesn't really make any difference as far as how large that number happens to be. So 1 times 3, because our common ratio is 3, and we're trying to figure out what n is. We don't know, so it's just n minus 1. Okay, and we're saying, well, 2,187 is the last number in that sequence of numbers. So I want to figure out what position does 2,187 hold in the sequence. So now we need to solve this equation. Well, we still have 3 to the n minus 1. I'll just take that 1 in the front out. It doesn't really have much of bearing on this. But you can already see that this is something that we've done in the past. There's a lot of different ways you can go about this. If you know what 2,187 is, this actually does have 3 as a base, and you can raise 3 to that base and get 2,187. If you were not able to figure that out and you had a calculator and we're going about it that way, I'm going to do it this way instead. But I will say this just one more time. 3 to some power does give you 2,187, and then it's just a simple solving with the exponents like we've done in the past. But let's say that you weren't able to see that. So then you could apply the logarithm to both sides. So ln of 3 to the n minus 1, and then ln of 2,187. All right, so then I would take the n minus 1 and place it in the front. And we still have ln of 3. So now we would say n minus 1 is equal to ln of 2,187 over ln of 3. And you could use your calculator here. But you'll find that n minus 1 has to be equal to 7, meaning 2,187 is the 8th term in the sequence. And just to reiterate, I really went the longest path probably that you could on this problem, just to make sure that you saw an example if you weren't able to do any of that in your head. So we know that 8 is we have 8 total terms in our series, and it is finite. It stops at 2,187, begins at 1. So to find the sum, so we're going to find sum of the 8 terms that we're working with. So I'll just put an 8 right there. It's not that big a deal. 1 minus, okay, and then r right here is -3. So I'm going to go ahead and use the -3 now. Okay, and we know that we're going 8 terms. All over 1 minus -3. Okay, and you can work all that out. You can use a calculator. I'm okay with that. And you come out with -1,640. For our sum. Which, if you think about it, that makes sense because the last term in our sequence, in our series, is the largest number, but it's negative. So it's probably going to have a negative sum total. If we went to the next term, then we'd probably go back into the positives. One thing I do want to mention, don't let this throw you off how I wrote the formula for the sum of a finite geometric series. I think in your notes it's written with the ace of ones in front, and 1 big parentheses around these. That's fine too. I'm just kind of writing it a different way because, 1, that's my habit, and 2, you may see this later on in other textbooks or from other teachers, and I just don't want to throw you off. All right, but there's example 6. Okay, part B, just working with the sigma notation. So once again, we'll plug 1 in. So we have 2 to the 1 minus 1, which is 2 to the 0, which is 1. So our first term is 1. Okay, and then we'll do the exact same thing. Now we're going to plug in 2 in place of that. So 2 to the 2 minus 1, which is 2 to the first, which is 2. So we know we're going to be adding 2 now. And then we're going to do one more time. 2 to the 3 minus 1, 2 squared, which is 4. And I bet you know this is geometric. So you can already see that there's going to be a pattern from here. So really all we need to do is just kind of figure out what the last term. So if we were to plug in 7, that'd be 2 to the 6th, which is 64. So plus 64 at the very end. So there's our series that we're trying to find the sum of, which we don't need all that, but just wanted to list that for you. First term is 1 again. So then 1 minus we're multiplying by 2. So our R value is going to be a 2. There's 7 total terms, all over 1 minus R, so 1 minus 2, because you can see we're multiplying by 2 every single time. Okay, R is equal to 2. If you were to use all that and crank it out, you should get 127 for that sum. All right, example 7, part A. Looks very similar to the one we did before, with the exception of this top is not a specific number like 7, it's infinity. So now we have an infinite geometric series. So just like we would do earlier, if I would plug 0 in, 1/2 to the 0 is 1, 5 times 1 is 5. And then we would add, well, if we put 1 in, that'd be 5 times 1/2, which is 5 halves. If you want to do another one, you could, but you can see just multiplying by 1/2 every single time. So it looks like that's our series that we're trying to determine the sum of. Now remember, this goes on forever. So what we notice though is that R equals 1/2, which is important for an infinite geometric series, because remember we talked about earlier, the only way you can find the sum of an infinite geometric series is if R is between -1 and 1, which we have in this particular case. So now to find our sum, it's just our first term, which is 5, over 1 minus our R value, 1/2. So that would be 5 over, well, 1 minus 1/2 is 1/2. So our sum for this infinite geometric series, it appears to be converging to 10. All right, part B. I hope this looks familiar to you. This is a problem that we did, I believe it was the first day in this unit in sequences and series, where we had the 0.55s. So if you were to add all of these up, notice that first of all, from one term to the next, it appears we're multiplying by 1/10 each time. So therefore, our R value is 1/10. Since R is between -1 and 1, we can determine the sum. Our first term is 5 over 1 minus 1/10. So this would be 5 over 9/10, which is 50 over 9. Okay, which consequently is the same thing as 5.5 repeating, if you write that as a decimal. And this is where, if we were in class, we could have a really neat discussion. I say neat, that's just for math teachers, sorry. We could have a cool discussion involving infinite geometric series and decimals and determining equivalency and things of that nature. So that's kind of a cool discussion. If you'd like to have that with me, you're more than welcome to. But just to keep this video a little shorter, I'm not going to go into it right now. But those of you who want to, I'm available for tutorials. Okay, last one. I need to make sure I do have one of these on there. Once again, you can see this is certainly a geometric series. We're multiplying by 3 each time to go from one term to the next, and it goes on forever. Okay, it's an infinite. So if we were trying to determine the sum, let's just say that you did. Well, then you'd be saying, okay, well, 2 over 1 minus 3, because it's infinite. And then you'd be, well, it's 2 over -2, which is -1. That sounds kind of weird. You're saying that 2 plus 6 plus 18, right? If we're trying to determine the sum of that series, and really it should be pluses in the middle. Let me put that in. That's bothering me. I know it says on your notes as commas, but it's infinite geometric series. Okay. So obviously 2 plus 6 plus 18 is not -1. Well, remember, for those infinite geometric series, R has to be between -1 and 1, which is certainly way larger than 1. Therefore, what I want you to say, which, here's a little therefore symbol, For our purposes, therefore, the sum diverges. All right, hopefully everything was clear to you guys. You guys have a great day. Stay out of the trees.